Okay, so, well, I'm hoping this is going to work pretty well for us. This is kind of different for me, probably also for you. So today we're going to be going over exponents. We've already talked a little bit about them. We already know how to do something like 2 squared. That's pretty simple. We just say that this is whatever this number is times itself this many times. So 2 times 2. Again, very simple. And of course, if we multiply 2 times 2, we're going to get 4. So 2 squared ultimately becomes 4. We can also say something like 5 cubed. Okay. Well, in the same way, we say it's whatever this number is times itself this many times. So it's 5 times 5 times 5. So 5 times 5 is 25 times another 5 is 125. Or we say that 5 cubed ultimately becomes 125. Again, very simple. We already know how to do this. What we're going to be talking about today is how these powers, these exponents, relate to variables. We've been talking a lot about variables lately, and we're just going to be getting more and more into their specific rules when we do things like, exponents and when we divide them and whatnot. Okay, so let me clear this off real quick. All right. So, just like what we were just saying, if I have something like x squared, what I'm saying is that this is x times x. All right. Well, what we're actually saying here is that these x's both have an exponent of 1 on them. We don't usually write that exponent of 1 because there's not really a reason to. If we just have x, we understand that it is just x to the first power. We don't need it. Just like if we're multiplying something by, saying this is 1x, we don't need to put that 1 there. We already understand that it's being multiplied by 1. Okay. So, we can say that x squared is really x to the first times x to the first. So then we can say, all right, well, x to the first times x to the first, that's just x squared. But why do we say that? Well, what we're doing here is basically taking these powers and we're adding them. So 1 plus 1 equals 2. In the same way, if I had x to the, 5th, that would be x to the first times 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 x to the first. So 5 of these things. And again, what we're saying here is, all right, this is x and x and x and x and x. How many of them do I have? I have 1, 2, 3, 4, 5. We just add up those powers. And yeah, it's x to the 5th. Okay, this, as we see it here, not very useful. This is basically what we are saying when we have simple powers like this, but it's not very useful just like it is right here. So let's see how it is useful. So again, I'm going to clear this off. Okay. So what if I have something like x to the third times x to the second? Okay, Well, like we just said, we can break each of these down into their basic components, into those separate x to the firsts. So x to the third, I break down into x to the first times x to the first times x to the first. Okay, that's my x to the third right there. That's done. Then my x to the second. Well, that just means that I'm multiplying. Again, we're multiplying here. I'm multiplying by x to the second, so times another x to the first times x to the first. Again, that's two of them. There's the 2 that we have here for x to the second, and the 3 that we have here for x to the third. And altogether, if we count these up, that's 1, 2, 3, 4, 5. Again, x to the fifth. Now, do you need to separate them out like this? No, not at all. In fact, I would hope that you don't have to do this. This would just be wasting a lot of time. What you should do instead is just say, all right, what is this? This is x to the third, this is x to the second. Just like we add up the exponents here, you can add up these exponents here. So 3 plus 2 gives us 5. So this really becomes x to the fifth. Don't need to do this right here. This is just me expanding it out so that it makes a lot more sense. Okay. So once again, let me clear this off. Okay. So what about if we have more than one variable? All right. So we have x to the second times y to the third times x to the fourth. Well, just like when we're talking about like terms, when we're combining our like terms, we're going to do kind of the same thing here. We just want to have the x's go with the x's. We can't really combine them too well with the y's here. You'll see how we actually do, but it's not really going to add with their exponents. What we'll say is we have x to the second and x to the fourth, and together those we add their exponents. So 4 and 2 is going to get me x to the sixth. And then we are multiplying times y. So this is just going to carry over as y to the third. Now notice that I don't have a dot between x to the sixth and x to the third. We don't necessarily need that. If we have two numbers right next to each other, we understand that they are multiplying. The only reason I wrote it over here is because I wanted to show y'all that we're starting out by multiplying. But when you write your answer, you should really have it like this right here. Just simply x to the sixth, y to the third. This would be our variables simplified, basically. It's a easier way to write these, and it's the more standard way to write these. Okay. However, when we're, and what I want you to understand from this is when we're doing math, so multiplying, dividing these things, when we're doing math with our exponents, we just want to look at the ones that are similar, the ones that are like terms. Okay? So let me clear this off again. Like I just hinted at, not only can we multiply these things, we can also divide them. So, and I'm going to start this over here since I want to have some room over here to show some things. Divide, of course, we can have a fraction. Let's say I have x to the fifth over x to the third. Okay. When we multiplied things that had exponents on them, we needed to add those exponents. Well, dividing is kind of the opposite of multiplying, isn't it? And we're going to do the opposite of what we did before. So again, when we multiplied, we add, and when we divide here, we are going to subtract. Again, it's opposites. So again, we look at our exponents. We say this is 5 and this is 3, and we're going to kind of treat this division bar as subtraction. So we're going to say it's 5 minus 3. And let me just write that over here. 5 minus 3. You might wonder why I'm being so, I guess, specific with this. Getting really down to the nitty-gritty details, like why I'm writing this negative here. You'll see in a minute when we get to some other exponents. Anyway, so 5 minus 3. 5 minus 3. If we subtract those two, we get 2. So our answer here comes out to be x to the second. Again, we just subtract. That's it. Okay, so clear this off. What if we have mixed variables, like we did before? So let's have x to the 7th, y to the 4th, over, I don't know, x to the 5th, z to the 2nd. All right, so once again, when we're doing these things with exponents, we want to just pay attention to the ones that are like terms. So my x's match. My y and my z don't match with anything, so they're not really going to be doing much. It's my x's that match. All right. So, when I go ahead and do this, I'm going to be looking at my exponents, just like before. 7 minus 5 is going to give me x to the second. Now you might be wondering, well, there's an x up here and there's an x up down here. Do we put it up here or do we put it down here? Here's an easy rule. Whichever exponent is larger, so the one on top or the one on bottom, that's where you want your answer to end up. So the one on top here is larger, so I want my x squared to end up on top, along with that larger exponent. Okay. And then y, nothing happened to it, so it stays here, y to the 4th. And z, nothing happened to it. It's still z to the 2nd. But this x down here, it's gone. We already subtracted it. We don't have to have another x down here. It's completely gone now. It has already acted on this thing up here. So this would be our final answer right here. Okay. So I'll clear this off. All right. So let's see one in the other direction. Let's have x to the 2nd on top and something like x to the 8th on bottom. Like I said, the rule of thumb here that's typically the best way to look at this is to say, all right, whichever one has the larger exponent, so in this case the one on bottom, that's where our variable is going to end up. So we subtract here, and we say that 8 minus 2, we always subtract the smaller one from the bigger one. So 8 minus 2 is going to give us 6, so x to the 6th. Then it's going to end up on the bottom. Okay, but what do we have left on top? We said that this thing is already acted, so we're not going to have an x left over. So what do we have left over here on the top? Well, when you eliminate everything on either the top or the bottom, this works for either one. If there's nothing left on top, we put a 1. Again, if there's nothing left on bottom, it'd be the same thing. We just put a 1. All right. So this would be our final answer here, and you have to have that 1 on top. basically what we've said is we've divided everything out of here. So this is kind of like saying, if I expand this out a bit for us, x squared on top, I can separate x to the 8th out a bit as x squared times x to the 6th. Again, if we were to multiply these two back together, 6 and 2 make 8. And so that would be our x to the 8th. We'll just separate this real quick so we don't get mixed up. Okay. And I don't want that anymore. Alright. So, just like if we were canceling things out when we're multiplying, if we remember back to there, we would say that this is now just gone because it matches up with this. Well, what we're doing there is we're saying this is divided by this. This is one thing divided by itself, and anything divided by itself is always going to be 1. And that's where our 1 comes from. Okay. Do I want you to do it this way? No. This is how I'm trying to explain why we get this 1 here. I'd rather you just say, alright, what is 8 take away 2? It's 6. Which one's the bigger number? It's on bottom, so that's where my x ends up. Alright. So let's clear that off. Alright. So we can multiply things with powers. We can divide things with powers. We can also take a power and raise it to another power. So we say that this is x squared quantity cubed. The whole thing is being raised to the 3rd power. So let's think about this real quick. At the beginning of lecture today, we said that when we take something to a power, it's like multiplying this thing by itself this many times. Alright, well, that would mean that we have x squared times x squared times x squared. Alright, well, we then said that if we are multiplying things with exponents, then we can add those exponents together. So 2 plus 2 plus 2, let's see, that's 2 plus 2 is 4, plus 2 is 6, so that's x to the 6th. Now, a much easier way of saying this is to just take this exponent here and this exponent here and multiply them. Because 2 times 3 is x to the 6th. So, this is how it works. This is, just kind of what I want you to do right here. Again, this is just me expanding it out so that it makes more sense. Okay. So remember, though, that this only happens when we have a power to a power. So this power right here is being raised to the 3rd power. And typically what you're going to be looking for is parentheses when this happens. All right. So what about if I start combining these ideas together? Let's have, I don't know, x to the 3rd, y to the 5th, z to the 4th, and then let's just have like a number here. All over 6, x to the 2nd, y to the 7th, z to the, 1st. And then let's raise the entire thing to the 3rd power. All right, well, this is just an expression. We don't have equal signs, and like I've said, when we don't have equal signs, we're looking at expressions. And when we're dealing with expressions, we want to use our order of operations to, condense them down, get the actual values, simplify them. So what we need to do is we need to follow that order of operations. And our first thing in order of operations is, of course, parentheses. We want to do what's inside of the parentheses before we do anything else. Okay, well, what are we doing inside of these parentheses? We are dividing. So we want to do this division first. All right. We'll see. The first thing we come across is 2 over 6. So 2 divided by 6, we can reduce that. Both of these have 2 in common. I can take the 2 out. 2 divided by 2 is 1. 6 divided by 2 is 3. Okay. Then I have my x's. I'm saying that this is x to the third divided by x to the second. When I divide things with exponents, I need to subtract those exponents. So 3 minus 2 is going to give me x to the first. The larger one is on top, so I need to put my x on top. We move on to y. Y to the fifth divided by y to the seventh. I need to subtract these exponents. 7 minus 5 is going to give me y to the second. And I put my y on the side that has the larger exponent, so that's going to be on bottom. Y to the seventh is larger. And then z to the fourth divided by z to the first. Well, that's 4 minus 1, so that's z to the third, and it goes on top because that's where my larger exponent is. Okay. So that's one part of this taken care of. But we have to remember that we also have something else going on the outside, and that is this exponent. It's still all being raised to the third power. So let's see. What happens when we have these numbers all raised to the third power is everything separately gets raised to the third. So this 1 gets raised to the third. We don't really need this 1, though. Anything times 1 is itself, so x times 1 is still x. And hey, even if we had raised that 1 to the third power, 1 times 1 times 1 is still 1. So we don't need it right there. But we're going to raise this x to the third power. We're going to raise the z to the third power. And like we said, we multiply those powers to get z to the ninth. Okay, we raise 3 to the third power, which means we're going to get, let's see, 3 times 3 is 9, times 3 is 27. And then y to the second raised to the third power. We multiply those powers, and we get y to the sixth. Okay, and then just to check and make sure, I don't see anywhere that we can simplify this any farther. I don't have any more that I can divide out of that, and we've already divided it out here. I have no addition, no subtraction, no anything else going on, so this would be my final answer. Okay. So clear that off. I hinted at something a little bit. Didn't really show it to us yet, though. When we have powers, we're used to seeing them as just being something like this, like x squared. However, we don't necessarily have to keep them in the positives. We can have exponents that are negative. So let's go back a little bit. If we have something like x to the 4th divided by x to the 6th, or I guess x to the g, let me try that again, x to the 6th. We say that 4 and 6 minus 4 equals 2, and we're going to put it on bottom. So this would be nothing left on top, so 1 over x to the 2nd. However, this is actually another way to write something else. If we think about it, why have we been just dropping something to the bottom? Really, this is 4 minus 6. And what is 4 minus 6? Well, 4 minus 6 is negative 2. So this would be x to the negative 2. However, when we have a negative exponent, what this is telling us when it is negative is that this is what's called the reciprocal. If we remember back to when we, I'll put a little division here, when we remember back to fractions, and when we divided fractions, we had this term for when we divided by fractions called multiply by the reciprocal. And what we did was we just said, hey, flip this second number. And so this would become 2 over 3 multiplied by 4 over 1. Okay, well, 1 over 4, the reciprocal of that is 4 over 1. Reciprocal means that we're taking the inverse of that number. It's the, not necessarily the opposite, but it's kind of like thinking like that. A whole number 4, the opposite of that would be 1/4. Okay, so like here we're multiplying by 4, here we're basically dividing by 4, you know. All right, so when we have these negative exponents, we're saying that we're taking the reciprocal of this number right here. An easier way of saying that is to put this number under 1 like we already have here. That's why I've been telling you that when we get something like this where the larger number's on bottom, we just put that number on the bottom, because I don't want you to have to think about this right down here too much. Okay? So let me clear this off real quick for us. So if I have a negative exponent, something like z to the negative 4th, and I want to convert that into something that does not have any negative exponents, because it's always kind of nice to have nothing but positives. If I want to convert this, all I say is that it's 1 over z to the 4th. That's it. This negative just means put this thing under 1. It does not mean anything else, and I'm not even going to say the thing that most people make the mistake of doing, because I don't want you to make that mistake as well. Okay, so if you see something to the negative power, it just means put it underneath 1. Now, if I have something like this instead, x to the 2nd over z, I don't know, maybe to the 3rd. Powers don't matter here very much. And this whole thing is raised to the negative 1. Okay, like we said, reciprocal means flip something. So just like when we were talking about the dividing two fractions and we take the reciprocal, we're going to take the reciprocal of this thing, which just means flip it. So z to the third over x to the second. Once more, reciprocal. All a negative exponent means is take the reciprocal. Make this thing flip. That's all it means. Nothing else. Okay. Another example of this. Let's say that I have something kind of similar to the last one. Y to the third over x to the second. And I'm going to raise this whole thing to the negative 2. Okay, well there's two things I really have to do here. First, I need to do something because I have this negative. Again, that negative there just means that I'm going to take the reciprocal. It does not mean anything else. So this is going to become x to the second over y to the third. Okay, so that's all that negative makes me do, is it just makes me flip that fraction. Then I still have the second on the outside. All I've done is I've taken care of the negative. I have not taken care of the actual power. So everything inside of here needs to be raised to the second power. And like we said, when we raise a power to a power, we multiply. So x to the second raised to the second will be x to the fourth. Y to the third raised to the second will be y to the sixth. And there's our answer. Okay, but I want to stress, I can't tell you how many times I can tell you this, and still there's going to be somebody who doesn't do it on the test. That negative just means flip. That's it. And then, once we get that negative gone, we can do whatever else we need to do with this exponent. But we have to flip first. Okay, let me... Whoops, that's the wrong thing to do. Get rid of that. Okay. So, let's see. Let's stick all of our concepts that we've learned together into one thing now. I'll have x to the fourth, y to the third, over z raised to the negative third times let's see, x, I meant to put a y over here, y to the fifth. Okay, x to the seventh, y to the fifth, z to the fourth, all over x to the second, z, and then this thing raised to the second. Okay. So this is going to include everything that we've gone over so far. Again, there are no equal signs here, and when we do not have equal signs, that means that we are just dealing with an expression. And if we're talking about an expression, we want to focus on using that order of operations. So, first things first, do what's inside the parentheses. Okay, so let's go to our first set of parentheses. X doesn't have anything that's matching up with it. Z doesn't have anything that's matching up with it. Y is the only thing that has anything that matches. Again, we're looking for things that are common, like terms. So we do our 5 and 3. 5 minus 3 is going to give me 2. And because my larger exponent was on the bottom, I'm going to put that y to the second on the bottom. Alright. Z, again, nothing happened to Z because nothing matched up with it. And X, nothing happened to it because nothing matched up with it. However, we still have this, whoops, that should be to the fourth. We still have this exponent on the outside, so we got to remember to keep that. Alright. This one. Let's do this fraction. Y doesn't have anything that matches up, but X and Z both have things that match, so we'll do those. X to the 7th divided by X to the 2nd. That gets us X to the 5th, and it's going to be on top because my larger exponent was on top. Again, nothing happened to Y. We're just going to have Y to the 5th still here. Then, we have Z to the 4th divided by Z. Well, 4 and 1, 4 minus 1 is 3, so that's Z to the 3rd on top. And I apologize for my handwriting so far. It's kind of hard to write on this tablet. But Z to the 3rd goes on top because my larger exponent was on top. And what do I have left on bottom? 1. And I'm going to keep it over 1 because I'm still dealing with another fraction over here. Okay. And I'm going to move this up so that we have enough space to work here. Okay. So, now that we've done the things inside of our parentheses, we need to do our exponents. So let's go ahead and do those exponents. First things first, this first one here, this first set of parentheses has a negative exponent on the outside, so we're going to need to flip everything and then raise it to the 3rd. So this is going to flip. Z and Y are going to come to the top. X is going to go to the bottom because we flipped this. And then we're going to raise everything to the 3rd. So Z was originally to the 1st. 1 times 3 is 3. So it's now Z to the 3rd. Y to the 2nd. 2 times 3 is going to give us Y to the 6th. X to the 4th. 4 times 3 is going to be X to the 12th. Okay. And then over here, we are just going to need to raise things to the 2nd power. So X to the 5th raised to the 2nd is X to the 10th. Y to the 5th raised to the 2nd is going to also be X to the 10th. I'm sorry, Y to the 10th. Z to the 3rd raised to the 2nd is Z to the 6th. And then 1 raised to the 2nd is still 1. Okay. So, now that we've gotten this, we can actually multiply these things together. And again, let me move this up so that we have some space. Okay. So when I go ahead and multiply these things, again, I'm looking for my like terms, the things that are similar. So x's we're going to multiply with x's, y's we're going to multiply with y's, z's the same thing. Okay, so on top, z doesn't have... Oh, wait, no, yeah, it does. Z to the third and z to the sixth match. So when we do this up here, z to the third and z to the sixth, we add those two things. 6, 7, 8, 9 is going to be z to the ninth. Then we have y to the 6th and y to the 10th. That's going to give us y to the 16th. And then we have x that doesn't really match up with anything on top. Okay. Then on the bottom, we have x to the 12th times 1. Well, anything times 1 is itself, so we have x to the 12th on bottom here. And now there's only one thing left to do. And that is to simplify this fraction. We have x to the 10th on top and x to the 12th on bottom, so we can divide those again. So x to the 12th is the larger one. 12 minus 10 is going to give us 2. So x to the 2nd on the bottom, y to the 16th on the top, along with z to the 9th. And there is our answer, finally. So I'll select everything here and bring it into view. Oops. Okay. So, quite a few steps that you can see here. However, as long as you understand your properties of exponents, these should not be that difficult. Really, what we're doing that's making this so long is we're going one step at a time. We're being very, very deliberate with our steps. We're making sure that we don't get lost. Okay? So as long as you know your properties of exponents, these should not be very hard. Just make sure that you take them slowly, because it is very easy to get yourself lost with these. Alright, so now let me clear the board once again. Now, there are other places that these exponents become quite interesting. First of all, we have the idea of powers of 10. Our counting system is based on powers of 10. I'm not going to go into that too much, though. However, if we have numbers, let's say 245, 670. Okay, if we have numbers and we want to multiply or divide them by a power of 10, it's very easy. Let's start with division on this one. So a power of 10 is just what it sounds like, 10 to some power. All this is telling me to do, all this 10 to some power is telling me to do, is to move the decimal this many times. And if I'm dividing, I'm going to be moving it to the left. So remember that when we divide, we should end up with a smaller number. So right now my decimal is starting out right here. If I move it 4 times to the left, that's 1, 2, 3, 4. So my new number is going to come out to be 24.567. Now, we don't really need the 0, but you know what I mean. So again, if we're using a power of 10, we're just talking about moving the decimal. Same thing if I'm multiplying by a power of 10. Whoops. So let's say that I have 327 multiplied by 10 to the third. Okay. Well, like I said, when we multiply or divide by a power of 10, we're just moving the decimal. The decimal's right here right now, so we'll move it 3 times. So that's 1, 2, 3. The decimal's going to end up there. And we'll just fill this in with some zeros. Okay, and that's it. So why am I showing you these powers of 10? Well, it's because they become very useful in something called scientific notation. And scientific notation itself is very useful for doing math with. Let me show you the basics, though. So what scientific notation is there for is to take very large or very small numbers and compress them down into things that are easier to deal with. I'll give you an example. One of the most popular ones that you'll see out there is called 3 times 10 to the 8th. Okay. If I were to add the rest of this to it, meters per second, this is the speed of light. Now, what does this represent? This is 3. Like we said, times 10 to the power means that we're going to move this decimal. So the decimal starts here. 1, 2, 3, 4, 5, 6, 7, 8. So the decimal is going to end up here. Fill in these zeros here. And we get quite a large number. So this right here, what we have is the scientific notation of this just integer. This is a lot easier to write down than having to write down all these zeros. And in fact, this 3 times 10 to the 8th is a lot easier to do math with as well. And again, I'll show you how to do that math in a second here. Let's just go over the basics of scientific notation. So let's say I want to go the other direction. Instead of having a number in scientific notation, I want to take a number and put it into scientific notation. So something like 3, 4, 5, 0, 0, 0, 0, 0, 0, 0. Okay? Very large number. I don't want to have to write this out a whole bunch of times. So what I do to put this into scientific notation is I say, all right, the decimal's right here right now, and I want to move this 3, 4, 5, 6, 7, 8, 9. I want to move this until I get the decimal to have only what we call one significant digit in front of it. Or for the purposes of this class, just one digit in front of it. Okay? So in this case, we moved the decimal until we got just 3 in front of it. That means that we've condensed this down to just 3.45. Much easier number to deal with. Now we still need to write how many powers of 10 we move that decimal. So times 10 to the, let's see, we moved it 9 times, so 9th. There we go. If we were to do this math right here, 3.45 times 10 to the 9th, well, we know that powers of 10 just move that decimal, and it would give us this thing again. Okay, so this is much, much more compact, much, much more easy to write, and again, once we get to it, much easier to do math with. What if instead of having a very large number, we have a very small number? Can we put it into scientific notation? Yeah, I already said we could. So let's say that I have something minuscule. 0.0000025. Tiny, tiny number. Well, just like we did with the other one, what we want to do in order to put this into scientific notation is to move this decimal right here until we only have one digit in front of it. So 1, 2, 3, 4, 5, 6. I now only have one digit in front of it. That's the 2. All right. So now my new number is 2.5. Much, much simpler. And then I need to say times 10 to the, let's see, how many times did I move that again? 1, 2, 3, 4, 5, 6 times. Now, we need to remember that we moved the decimal a different direction here. And to show that direction, we're going to say negative. Again, the negative shows that we're taking the inverse of times 10. So what would the inverse of times 10 be? It would be divide by 10. And when we divide by 10, we get smaller numbers. So the rule of thumb here kind of is if you have a small number to start out with, you're going to have a negative exponent for your scientific notation. If you start out with a really large number, you're going to have a positive number for your exponent in your scientific notation. That's just a good rule of thumb. Okay. So, one more thing to show y'all. Scientific notation is extremely useful because in science, where this is really used, we typically have very large or very small numbers that we're trying to do math with. I'll just come up with two numbers right off the top of my head. Let's say that I have 6.0 times 10 to the 50th. Big, big number. And I want to divide it by 3.0 times 10 to the, oh, I don't know, 30th. Okay. Well, I can look at this as two different parts. I'll basically just split it down the middle here. All right. This is 6 divided by 3. So this part, 6 divided by 3, is just going to give me 2.0. This part over here, I'm dealing with powers. And when I divide powers, I know that I subtract those things. So 10 to the 50th and 10 to the 30th, I subtract 50 minus 30, and I'm going to get times 10 to the 20th. So instead of having to go through and look at that huge number and do lots and lots of place moving and whatnot, I can just say, hey, divide these numbers and then then subtract these decimal, or not decimals, subtract these powers, and I get a very quick answer. And it's accurate too. It's not like we're taking any shortcuts here. It's just a very easy way to deal with large numbers. Okay. So, that is basically all I have for today. Now, you are going to be taking a quiz on Alex over this stuff. And I can't really control what you're able to use. So, calculators, whatever, you can use those. But you will need a password to get onto this quiz, and that password is capital E capital X, capital P. That is your password to get into the quiz. Okay? So that's it for today. I hope this was helpful. I hope that this didn't just confuse us with the format. And I will see you all later. Have a good day and be sure to take that quiz. Goodbye.